general relativity, step by step. We've got an equation here that says that gives us the second derivatives d2 by d tau squared of the components of the separation vector n, separation vector of two objects moving along geodesic lines. However, what this equation doesn't do, or what it's not misleading exactly, but it is what it is. The problem is that we have not accounted for the change in basis vectors as these objects move through space-time. So there could be two objects whose separation vector is constant, but for one reason or another we have chosen a coordinate system which is itself varying, and so this term here comes out to be non-zero, even though the two particles have a constant separation vector. What we need to do here is to work out the true derivative. And we need dn as a vector by d tau. Actually, we need the second derivative, don't we? But I'll have to work out the first derivative first. We need d2 by d tau squared of n. And that's the true derivative. But to do that, I need to work out first the first derivative, d tau, and I'll work it out. I'll work out the components alpha of that. So how do I do that? Well, we'll just write out the definition of it. I'll leave the alpha off for the moment. So it's d by d tau of, and then n is just n alpha e alpha, which is equal to, we'll just differentiate each of those terms in turn. So we've got n alpha d e alpha, that's a vector of course by d tau, plus e alpha dn alpha by d tau equals, well, I'll write this one down first. It's e alpha, this is the basis vectors, dn alpha by d tau, plus n alpha. Now I can't just have rate of change of e, the basis vectors with respect to tau. I need to link it to the coordinate system. So I'm just going to say dx mu by d tau, because I know what that is, times di e, which axis have I got? I've got alpha by di x mu. So what I'm doing here is I'm using the total derivative law to differentiate d by d tau of e alpha. There we go. Which equals e alpha dn alpha by d tau plus n alpha, and this term here is u mu, because by definition that's the forward velocity of my particle, times di by di x mu, this is summed over mu of course, e alpha, which equals, well, we can use the definition of the Christoffel symbol here. So it's e alpha times some stuff in brackets, and what have we got? We've got this term here, dn alpha by d tau. We've got an n plus n alpha. We've got a u mu here, and we've got a Christoffel symbol. Oh dear, now let me just get this straight. It's contracted on the top, and what have we got on the bottom? We want to sum over, we're summing over mu anyway, and we also have we want to contract on this term here, which is an alpha. Oops. Now straight away I've got a problem here, because look, I've got an alpha here, an alpha here, an alpha here, and an alpha here. I'm trying to contract on this alpha here. What have I done wrong here? Oh, I've got alpha's doing too much work. I'm going to call that something else. I'm going to call that sigma, and I'm going to call this one sigma here. Now I've got a repeated sigma. The alpha contracts with this one as it should do. The mu down there contracts with the mu here. That sigma's there. That alpha's free. Hang on a minute. I'm still not right, because that alpha should be free Oh no, it isn't free. We've got this alpha is free here, and this alpha is free here, both of which are contracting on this alpha down here. That's correct. That's correct. Equals. So d by d tau, just copying from here, copying from this equation here, of n alpha e alpha equals this thing here times e alpha. So we may as well just write dn as a vector by d tau alpha equals just this thing in the brackets, which was dn alpha by d tau plus n sigma u mu, where u is the forward velocity of the object following the geodesic. There's Christoffel symbol. Alpha is now free because I'm not contracting with the alpha and my basis vectors there. Mu sigma. Whew. All right, that's quite a lot of work. I'm going to stop there. Stop.